This is the atmospheric circulation lecture for week 9 of the course. I'm going to go ahead and share my application screen showing you the PowerPoint lecture for the week. There are going to be 2 PowerPoint lectures for this week, atmospheric circulation and ocean circulation, and the lab that you're going to complete matches up with both of those. I'm going to so what I'm lecturing from is the mini PowerPoint. I'm going to actually go to the end first, similar to what I did with plate tectonics, so that you can see what we're working toward. I'm showing you the winds and the wind circulation map. You want to remember, of course, that there are 2 PowerPoints that cover atmospheric circulation. The main atmospheric circulation lecture, which is found under the content tab, that has all the embedded notes and the larger version of the PowerPoint. And of course, I'm lecturing from what's called the mini atmospheric circulation lecture that's found directly in the weekly folder for week 9. Focusing specifically on this figure, in lab number 6, you're going to be asked to fill in a blank earth with the latitude lines, with the wind names, with the pressures, and with the directions of the wind flow. This figure is a good way to check your work. There are a couple of other figures that follow after it, which also help you to check your work. But I just want to caution you. I know you want to fill in the lab and you want to turn it in and you want to get full credit, right? But if you just copy this material, you didn't learn anything. All you did was show that you could copy work. Of course, for an exam and being able to get through important material and understanding stuff, you need to understand the material. So please, please, please try to do the lab without using any help. Then go and check your work, okay? This figure and the next 2 figures that I showed you are great ways to check your work. But please absolutely try to give it a try on your own first. With that being said, the first thing that you're going to want to do is label the latitude lines of the Earth. So we know that the equator is 0, okay, 0 degrees. And then if you were to fold this in half, like a piece of paper, or just think if you could fold a pizza in half, the top and the bottom would match. So we must have a mirror image of there as we go northward to the North Pole and as we go southward to the South Pole. And sure enough, we do. The mirror image is 0 degrees to 30, 30 to 60, 60 to 90 degrees, okay? 0 to 30, 30 to 60, 60 to 90 degrees. The only difference is these are north, and these are south. Okay, so that's your mirror images with your latitudes. I'm just going to keep cleaning our figure up so nothing gets too messy. Next thing you want to do is start labeling the winds. So at the equator, which is the widest portion of the planet, you can actually draw a straight line without having the Coriolis effect come into play. It's going to be constantly hot, constantly tropical in its weather. The pressure systems are low, and so you don't have the Coriolis effect in application because it's a direct straight line. So the wind patterns are eastward, E equator, E east, so it's easy to remember. That means they start from the east and head westward, and they don't veer off, meaning they don't head to the right or to the left. They don't have a Coriolis effect. So we call those winds the doldrums, dull meaning boring. They're also named because of where they converge, where they meet, intertropical convergence zone. Clearly this is a tropical location because it's warm, converge to come together, and intertropical. So what you're having is warm air converging at the equator. So that's your first wind pattern, okay? That's at the equator. Now we have to start filling in our wind patterns from 0 to 30, 30 to 60, and 60 to 90. So there are 3 wind patterns, and they go east, west. My pen is hard to work here at the top. And east, that says east. You're going to notice that if we have an east here and an east here, then those easts have to have different names. So we also call this one the trade winds. So that's the trade easterlies. And this is the polar easterlies. So it goes east, west, east, but it's east trade, westerlies, and east polar. More importantly, because this is the northern hemisphere, we're going to go ahead and we're going to call those the north trade winds, or the northeasterly trade winds, the northwesterlies, and the north polar easterlies. So again, east, west, east, but of the northern hemisphere. Okay, if these are mirror images of each other, then of course this is a south, southeasterly, southwesterly, southeasterly, but this is a polar easterly, this is a trade easterly, and a southwesterly. So now we've gone 3 winds north of the equator, 3 wind patterns, and 3 wind patterns south of the equator. Similarly, what we've done is we've gone from 0 to 30 in either direction, north or south, 30 to 60 in either direction, north or south, and 60 to 90 in either direction, north or south. East, west, east, east, west, east. Next thing you want to remember, of course, is that we have 3 temperature-based zones on the planet. We have our tropical in the middle, centered around the equator. We have our temperate, which is where we live in New York. That's centered around 45 degrees, so right here in the center. And then our polar, north and south. So we have 3 temperature-based bands. If we take those 3 temperature-based bands, we should be able to match up our warms with our colds. Tropical should have warm, represented by red, both north and south of the equator. Polar should have cold, both north and south of the equator. But since air has density and it rises and falls based on the circulation patterns, warm must eventually rise and get cold. Cold must eventually fall and get warm. And the temperate bands, of course, are going to represent those that are sandwiched in the middle with have both warm and cold situations. Finally, we want to add pressures. We're going to use this next figure for the pressures. You're going to notice that we have low pressure at the equator. Why? Because it's warm. We're going to have high pressure at the poles. Why? Because it's cold. And if we're rising and falling with our warm and our cold bands, warm and cold bands, right? If that's going to happen, then of course you have to go from low to high to low to high. Mirror image, low to high, high to low, low to high. Next figure shows you the same thing. It reminds you that you have low pressures and high pressures in the warm and the cold areas. So low, high, low, high. Back to low, high, low, high. Warm, cold. Intertropical convergence zone where easterly winds begin. Starting then, of course, with our northeasterly trades and our southeasterly trades. Our northwesterlies, our southwesterlies, and our north polar easterly and our south polar easterly. So we go east, west, east. That is our wind circulation patterns. Now I'm going to go to the beginning of the PowerPoint. Again, we're using the mini PowerPoint. And we're going to try to break all of that material down so that we can better understand how it works. Now the term density, of course, you know already. The density of air is very similar to the density of water. You learned density in Lab 1 and Lab 5. If we're talking about the density of water, cold water is more dense. So air is the same. Cold air is more dense than warm air. Now we have 2 more types of air patterns that we're going to want to factor in. Is that air, whether it's warm or cold, humid or dry? Okay. Humid is moist and wet, almost like a liquid. Okay. It is less dense than dry air. There's less stuff in it, right? It's spread out in space, so its density is less. for the same concepts that ice is less dense than liquid water. Okay, so the least dense air is going to be warm and humid air. So where's that least dense air going to be found? The tropics. What kind of pressure do you have there? Low pressure. So that should all match up with the wind patterns that we just discussed. Now, wind patterns, of course, blow from either west to east or east to west horizontally across the planet. Of course, think about if you went in an airplane, you fly over in an airplane and the window gets cold, right? So if you rise up in the air as opposed to going horizontally, and we actually have a vertical circulation, there's also a change in temperature. It's warmest closest to sea level, closest to the Earth's surface, and colder as you rise up. So if we're going to rise up and cool, air will expand. If you're going to fall down and warm, you're going to compress. Okay, so now we have two factors, the horizontal and the vertical, both based on density, both based on temperature. If you were in a closed system, okay, think of like a house, and you had a hot heating source, okay, for the equator, let's say, it's situated in the center. The equator is going to be at 0 degrees latitude. Hot air will then rise toward the North Pole or rise toward the South Pole. It will rise up, but as it rises up, of course, it cools. So as it cools, it falls back down. So what's actually happening is the cold air at the polar locations, North and South Pole, is falling toward warm. You're going to see in one of the videos that we completed for you for Lab 6, we're going to dye some water. We're going to put some heat sources, what represents the equator, and we're going to put a bag of ice, essentially, which represents the poles. We're going to dye some water blue and red, and you're going to see that the blue falls and the red rises. So this figure is a great way to demonstrate exactly what we're doing with that lab video. The next component that we talked about with the winds was pressure. Remember, we had low pressure and high pressure. Low pressure is going to occur in the tropics and in anywhere that it's warm. High pressure occurs in the poles and anywhere that it's cold. So if it's cold, it's heavy, it's going to sink. If it's warm, it's light, it's going to rise. So low pressure systems rise and high pressure systems fall or sink. When we talk about those pressure systems, intertropical convergence zone, right? Low pressure. So now you see where those names are coming from. So we're remembering one more time that the low pressure is situated around the equator. And of course, since it's warm, it rises up toward the South Pole, toward the North Pole. At the North Pole, you have a high pressure. So it's going to fall toward the equator, only of course to rise and fall again. Second component that we want to add is something called uneven solar heating. Okay, so I'm going to go back and show you that main figure that we were focusing on. I want you to imagine that the sun is shining from exactly the right-hand side of the screen. Okay, if the sun isn't moving, we're moving around it, right? If the sun isn't moving and the sun's rays have the same warmth to reach the planet, the distance that that warmth would travel here is less than it would travel here, right? Or here. So the Earth is unevenly warmed, okay? It's warmed directly at the equator and indirectly at the poles. Let's go back to that figure that we just left off from. If it's warmed indirectly, then what that's showing us is that, of course, we have the same amount, look, same amount of sunbeam. The same amount of sun covers a smaller space because it's direct heat, so it's more hot there in the equatorial regions or tropical regions, and the coverage is greater at the poles because it's on an angle. Think of a flashlight. If you were to shine a flashlight into a straight path, it literally makes a really small square. If you put it on an angle, it makes a dim, larger square. So this is uneven solar heating, okay, which relates, of course, to the fact that we have warm tropical areas here and cold polar areas here. Not to mention the fact that we are circulating around the sun. So the seasons factor into that as well, right? The sun always stays in the center. We go around it, which then gives us our 4 seasons in a temperate area, 2 seasons in a polar and a tropical area. Regardless, though, of what season you're in, the middle of the Earth is always the closest to the center. So the center is always our tropical location. Let's put all that together. If our sun's rays are closer in the middle and further, whoops, I don't know what happened there. My computer's going haywire today. So one more time, if the sun's rays are closer in the center in the tropical zones and further in the polar zones, and since they're closer and further, we have cold versus hot air, we have uneven solar heating. The center of our Earth, centered around the equatorial regions, the tropical and subtropical regions are then therefore represented by warm. And that warm air is light, so it rises up, also because it has low pressure. Similarly, at the North and the South Pole, it's colder, it's heavier, it has to sink, also again, having high pressure. Now this is on a non-spinning Earth. In other words, things are literally falling straight down from the poles to that center equatorial region. That can't be the case because we're spinning. So if we're spinning, then we have to apply the Coriolis effect. And we're going to pause there.